Let's continue to look at some of the differences between Greenland circulation and Antarctica so that we can understand the differences in marine ice sheet instabilities at the two continents with glaciers on them. Here is a schematic again showing the polar seas. Ocean heat is found several hundred meters below the surface, as we saw, in the form of warm salty water. That's important. Surface waters are comparatively cold and fresh. So you can see the density of the water is very non-linearly dependent on temperature and salt. So you can create all kinds of circulations by putting warm salty water and cold fresh water in different places above or below each other to create instabilities and so on, which is important because if you're melting a glacier and the water can sink away, then new water comes in and brings new heat, which can continue the melting, right? Surface waters are comparatively cold and fresh. As we said, wind transports the heat towards the glacier. So in the southern hemisphere, if you remember your Coriolis effect, the tilting of the water is towards the left of the winds in the southern hemisphere and towards the right of the dragging wind direction in the northern hemisphere, which we call the Ekman drift. The thermohaline circulation ventilates the ice shelf cavities in this figure. So thermohaline circulation is basically temperature and salinity driven circulation. So the temperature and salinity together create density differences, and if you have heavier water on top of lighter water, the heavier water is going to sink and new water is going to flow into that region for mass balance. And this is how the deep ocean circulation is driven. We haven't gone into details, but some of you may already know, or you can Google it, or you can look at my other podcasts in the oceanography course or the ocean dynamics course. Okay, near the surface, winds drive the circulation, but deeper ocean, which moves so slowly that you cannot even measure the currents directly, is driven by these thermohaline circulations. And under the glacier, we are looking at melt rates of 100 meters per year in Antarctica and several meters per day in Greenland being generated by this ventilation, basically, which means the waters are seeing the surface and then going down and so on and so forth. Okay, so the Greenland circulation comes from the subtropics, whereas here we said this is a channel. So typically when winds try to drag the ocean, the amount of energy being put in depends on the continental boundaries. So winds want to drag it and put energy into the ocean, but you hit the other coast, then no more energy can go in. But when you have a circular channel like this, more and more energy from the winds can go in, and surface warming can penetrate much deeper all the way to the bottom, depending on how strong the winds are. So that also brings warm waters to the bottom. So this is going from west to east in this direction, and you have the Ross Sea Gyre here, the Weddell Sea Gyre here, Amundsen Sea, Pine Island, Bellinghausen Sea down here, and so on. So Antarctica ocean heat is contained in the Antarctic circumpolar current, which actually isolates the Antarctic continent from the rest of the ocean in many ways, because the exchange between this circular current and the other parts of the ocean is very slow. Warm water, about +2 degrees C, is present in the 400 to 700 meters below the surface. That is a massive amount of warm water that can do serious damage. At the surface, water is cold and fresh. Prevailing westerly winds means they're coming from the west going towards the east, in a clockwise direction, so in this direction, west to east, as I said. The Coriolis displaces the water to the north, so there is a divergence, water's moving away from Antarctica. and displaces the subsurface warm salty water to the south, so to going to the right. Okay, there are complicated east wind drift in the interior and west wind drift in the exterior, but we are kind of doing this without the details. So with climate warming in most of the world and cooling in Antarctica under the ozone hole, so the warming in Antarctica is not as rapid as the other parts. The winds are getting stronger, so the front between the subtropics and the polar front is moving northward. So they are displacing more warm water towards Antarctica. Okay, so there are complicated dynamics which are basically creating warmer waters to drift towards Antarctica and create these marine ice sheet instabilities or making them worse. The flow around Greenland, on the other hand, is largely related to this Gulf Stream that's coming up here up to Cape Hatteras, separating, going off as North Atlantic current into from the western part of the Atlantic towards the east, towards Europe, and then going north as the North Atlantic current. All these red colors are warm currents coming all the way in the Gulf Stream from the subtropics all the way into the Arctic. You can see these complicated gyres like the Beaufort Gyre. The Fram Strait is down here, and there is the Denmark Strait flow here, Davis Strait here, Labrador Sea currents, down here, Baffin Bay, and so on. So you can see that this circulation is very different than the circulation around Antarctica. And all of these are riding on top of additional complications called here. So you can see the less warming here. Now this is surface temperature trend, not the ocean heat content. In terms of degrees Fahrenheit per decade from 1990 to 2019. The ice albedo feedback we talked about, in fact, creates the so-called polar amplification. So the warming here is maximum here in the polar Arctic Circle. Okay, so you can see that the Greenland is getting pretty warm as well. Okay, so obviously the surface melting and the moulins and the runoff is massive in the Greenland compared to Antarctica. We saw that it's 300 gigatons per year over Greenland, whereas it's, the runoff is 0 over Antarctica. Right? Complicated issues. The Arctic warming is also creating additional complications by making the jet stream, we haven't defined it, it's basically the elevated, very strong wind in the atmosphere at the polar latitudes, which is like a referee between cold, high pressure polar air and the low pressure, warm subtropical mid-latitude air. And it is determined by how strong the gradient of temperature is from the equator to the pole. So when this polar vortex is stable, the jet stream tends to be quite straight, narrow, fast, and keep the cold air there. But when the polar vortex becomes wavy, then the jet stream becomes meandering, goes meandering a lot in the meridional direction. So it can bring cold Arctic air with it and also push the warm subtropical air north. So you can have Washington DC being at like minus 50 degrees on the really, really cold waves, and Alaska being much, much warmer than DC in those seasons in winter when these wobbles happen. So there is some ideas, it seems confirmed by now, that Arctic warming is in fact creating more wobbles in the jet stream, so the heat pumping into the Greenland is potentially increasing and creating the warming here. Right next to it there is a so-called warming hole, where it's probably related to this thermohaline circulation, but we will not go into those sorts of details. So you can see that there are massive differences between Greenland and Antarctica, and the processes are different in details. Marine ice sheet instabilities are different in details, but both are creating serious ice melt. That's what in the end matters. So the question is, who's going to accelerate more, and which one should we watch out for, or for more carefully in terms of sea level rise? We already mentioned 7 meters of sea level rise and some 56 meters of sea level rise locked up in Greenland and Antarctica respectively. So we really have to watch carefully how the two are melting away.